Hello, so today is section 1.2 and the topic is reflection and stretch. Before we dive into more graphing today, we're just going to define a couple more words to add to our knowledge on transformations. The first word is reflection. So this is a transformation where each point is reflected over a line. Specifically here, the lines that we're talking about is going to be, at least in this section, it's going to be the y-axis and the, x-axis and the y-axis. These are the two lines that you will be reflecting over. So what that may look like is we have our graph. We're going to have, some shape like that. It might reflect over the y-axis, so it's going to flip over and look something like so, or it might flip over the x-axis, if that is the flipping line, and you'll have a reflected image that might look like that. Okay? Next is something called invariant point. You did talk about this in PreCalc11. So as a refresher, this is a point on the graph that will remain unchanged after the transformation. So compared with the original, the transformed graph will have exactly the same point. It will be on the same x and y point. So as another example, if we have a graph that looks like this, for example, and we're going to flip it along the y-axis, then our graph is going to look like, our graph will look something like this, right? And that point right there, from the original to the flipped part, has not changed. And this is what we call the invariant point. Okay, since it does become very long to write invariant point every time, so I'm just going to short form that as IP. So what you'll notice about the invariant points is that it's any point on the line of the reflection is an invariant point. So in this particular case, since I am reflecting on the y-axis, so that invariant point sits right on that line. So let's look at some graphs now. Our first graph here is this one. I'm just going to zoom in a bit since it's so small. So we're going to graph y equals negative f of x, and f of x is given to us here in blue. So f of x is our base graph. I'm just going to keep out the blue. So this is our base graph, and we're going to be transforming it. Now looking at here, we're going to be multiplying our whole function by a -1. That gives us the negative sign. And our function basically is equivalent to our output, right? So our output is being multiplied by -1. Thinking back to our mapping, from our original points, nothing has changed with our input, so that will stay the same, but our output was multiplied by -1. So therefore our y value is multiplied by -1. Now at this point, we're just going to take different points from our original graph and then transform it. So there's -4, -3, -2, -3, and then we have 1, 0, and then we have 3, 4, and 5, -4. Transforming that over, x values have remained the same, but our y values have multiplied by -1, so you will need to change those up. And here we are. So now that we have our transformed points, we're just going to plot them in. So -4, 3, negative 2, 3, 1, 0, 3, negative 4, 5, 4. Now let's just connect the dots. Preferably use a ruler. I'm not using one here. There we go. So comparing the original in blue to the transformed in black, you'll notice that all the points have either moved up or, in some cases, down. So it has moved up and down. And looking at the points we have on the right, if you look at point letter C, I mean not number C, point letter C, you will see specifically that, hey, nothing has changed. If the point remains the same from the original to transformed, what do we call it? It is called an invariant point. If you forgot what IP stands for, rewind a couple minutes. Okay, so from our particular graph here, we saw that from our function, y, we multiplied our function by negative. Now, what happens when we do that? Well, our points either move up or down, and it gives us an image that is reflected. And since it's being flipped up and down, it is a vertical reflection. Remember, vertical's up and down. So in a vertical reflection, the output, so the output is our y value, of the function is multiplied by negative 1. The reflection is on the x-axis. So that reflection line, as you can see, is that x-axis, okay? So one thing that I've noticed before is that students do confuse x-axis or associate x-axis with being horizontal, which it is. So x-axis does point out the horizontal points. However, if you're reflecting on the x-axis, it is a vertical reflection, not a horizontal reflection. So just make sure you clear your mind on that. Next example here. Very similar, same graph, but instead of having the negative sign outside the function, it is now affecting the input. So similar to before, we have our x and y, but this time our x values are the ones that are being multiplied by negative. So here we do have A is, negative, not negative 2, negative 4, negative 3, B is negative 2, negative 3. This is exactly the same points as before. Okay. And when we change these over, we have 4, negative 3, 2, negative 3, negative 1, 0, negative 3, 4, and negative 5, negative 4. Oops. I said 4, but I wrote 5. Negative 4. So again, when we plot these points onto the graph, it will look like so. So the first point is now on the right side. Here, negative 1, negative 3, 4, and negative 5, negative 4. So connect these dots together. And you have this graph. As you can see here, this time the points are going from right to left or left to right, right? So points are moving horizontally. If you look at the points that we've mapped, there are no identical points between original and transformed. However, if you look at where we flipped over, since we're flipping over the y-axis, there is a point that lies on the y-axis. Any point that lies on the line of reflection is an invariant point right there. So looking at our example here, this time we have y equals to f negative x. And since points are moving left and right, we call this horizontal reflection. The input, also known as x of a function, is multiplied by -1. And this time, since it's a horizontal reflection, you are reflecting over the y-axis. Again, do not confuse the axis with the direction it's flipping. Okay, with our newfound knowledge, let's just look at a couple more examples. So this time we do just have this line here, and we are looking at y equals to negative f of x. Remember, when this negative sign is in the front, what do? It will be a vertical reflection. So in this particular case, all the points will flip over the x-axis. So I'm going to show you both ways of doing it. There's kind of two different ways. We're just going to start with the mapping method again. So let's just, since we don't have points picked out for us, we'll just have to find points that work. So there are 3 intersecting points here. I'm going to write this out in black. So we have 0, 2, oops. Actually, let me just show the mapping from the beginning. So x, y, since it's vertical, so x remains the same, y will be flipped. So it's 0, 2, 0, negative, oops, goodness, what am I writing here? -1, 0, and -2, -2. If you move these over, you will have 0, -2, -1, 0, -2, 2. Let's plot these points in here. Oh, I'm actually going to plot in red, so it's a bit more vivid. And then here. So if you connect these dots, you'll see that it has reflected over the x-axis. Or you could just think of it as, well, my line of reflection is on the x-axis, therefore the points must have just flipped over the x-axis like so. So from 0, 2, just mirror image it, reflect it down, voila, there we go. Okay, so with the next one, I'll do it with the shorter method. So this particular case, we have the negative affecting the input, so we know this time it is a horizontal reflection. In this particular case, since we are flipping on the y-axis, so instead of being here at -1, 0, we're going to flip it over to the other side so we know the point is there. Any point that is on the y-axis will stay as is, and then we can just graph it. Oops. Okay. So the invariant point here is right there. I think I missed the invariant point for the last question, so I'm going to go back up. So the invariant point on this one, since we're flipping on the x-axis, our invariant point is right there, the point on the x-axis. Okay. All right, moving on to something a little different now. So instead of having a negative sign in front of our function, we now have a number. So we could just apply the knowledge we had before. And with mapping, x, y, well, when the negative sign was in the front, it was a vertical reflection. So let's just put that value, instead of a negative sign, put a 2 in front. So now that we've done our mapping, we'll just put in some points. The points have already been nicely labeled for us. Oh, so it's -6, 4, -2, 0, 0, 2, 2, 0, 6, 4. According to our transformation, this will bring us to, I'm just going to write out all the x values first because nothing changed there. And then with the y, it's 8, 0, 4, 0, 8. Ta-da! Here are the points. I think it turns out better. I'm going to graph this in red. That's why I wrote that bracket there. So if you plot those transformed points, it'll be up there, down here, in the middle there, down here, and up there. And now it's just a matter of connecting all these dots. Okay, here we go. And you do need to state the invariant points. So from the beginning and end, we see that these 2 points there have not changed. IP. All right, next one here. Let's go with the same strategy. Again, we're just going to change our y value. And we have x stay the same, but the y is going to be 1/4. So let's just write that out again. So we have -6, 4, -2, 0, 0, 2, 2, 0, 6, 4. Oops, drawing these arrows properly. Again, x values have not changed, so I'm just going to write it as it is here. And then we have the y values. So that's 1, 0, half, 0, 1. Here are the points. So if we plot that in, we have, I'm going to write this in red, we have that 1 point here. And yeah, and the last one is at 6, 1. Connect the dots and you will see this. Okay, so here, ooh, it's asking for something a little different. It's actually asking us to state the domain and range. Ooh, need to refresh our minds on that. So what's domain and range? Domain and range. So domain are the possible x values, and range are the possible y values. Okay, so in this particular case, looking at our g of x, which is this red line, when we look at x values, we see that it can go from -6 up to 6. Those are all the possible values it can go. Okay, just from -6 to 6. So we'll say our domain is x has to be greater or equal to -6 and has to be less than or equal to 6. Our range, on the other hand, really just spans from 1 to 0. So in this case, we know our y values must be greater or equal to 0 and smaller or equal to 1. So that's our domain and range. Okay, so looking at these two pictures here, I'm going to kind of go out to it. We see that in the first picture, well, our W definitely has gotten pulled vertically, kind of taller, whereas in the second picture, it got squished, kind of like it was compressed down. So the words we use here is vertical compression or expansion. So compression would be our picture below here where it gets squished. So I'm just going to write here. So this is compression. Okay. Whereas the picture above, since it got kind of stretched out, we'll call this expansion. So a vertical compression or expansion is a transformation in which the distance of each y-coordinate from the x-axis is multiplied by a scale factor. So what that looks like in a kind of equation form is such. Y equals to, the letter to represent the scale factor is A. There's this number in front of the function. So as we saw before, if that number is between 0 and 1, so that's the second example that we had, you'll see a compression. So it's getting squished inward. So it's, something that's going inward like that. But if it is, if A is bigger than 1, then you're dealing with an expansion. So whatever you had is kind of pulled away from each other. It's going to look taller. Okay, so moving down here. In this next example, we see that we have a value in front of the x. So thinking back to when we had a negative sign in front of the x, well, we just multiplied the negative to the x value. However, when you have a scale factor affecting the input, then things are slightly different. What you'll actually have to do is, from your original, you will actually need to take that number and find the reciprocal. So in this particular case, it's 2. So this is the reciprocal of 1 over 2. So just to refresh your mind on reciprocal means you just flip the numerator and denominator. Okay? Let me just write that down really small. Flip denominator. Shouldn't pronounce it's denominator. Don't pronounce it denominator. Flip denominator and numerator. That will give you the reciprocal. Which brings it to 2x y. At this point, you'll just follow the procedure as is. In this particular case, we don't have marked points, but basically we could say these 5 points are our key points that we will be transforming here, which is -4, 4, 2, 0, sorry, -2, 0, and 0, 2, 2, 0, 4, 4. And let's transform this thing. So -8, 4. -4, 0. 0, 2. 4, 0. 8, 4. So let's plot this in. I will be plotting it in red again. Just show that. So that brings me out to 8. -4. That stays there. There. Let's connect the points together. Okay, so here are the connected points. Since this was expanded from that y-axis, so here is an invariant point. Okay. All right, looking at our next example now. Same thing with the mapping. So it's going to be reciprocal. Same points here. So that's, oops, a -8. -2, 4, -1, 0, 0, 2, 1, 0, 2, 4. Again, going to graph this in red. So everything, oops, kind of moved inward. Kind of moved. So the new W looks like that. So unlike the pictures we saw above, this time, this W got pulled sideways, outwards, and then got squished sideways inward to create a wider and narrower W. So this is called horizontal compression or expansion. It's where transformation, it's a transformation where the distance of, sorry, it should be of, not or, of each x coordinate from the y-axis is multiplied by a scale factor. So in this particular case, we have y equals to f, and it's the input that's affected, and the letter used is b, x. So this time, when b is bigger than 1, then the graph is horizontally compressed, what we call compression. You can think of it pushed inward like that. And when b is between 0 and 1, then the graph is horizontally expanded by a factor of 1 over b. Okay, so you do need to make sure you find the reciprocal before you figure out how it expanded. So whenever we're dealing with horizontal transformations, you do have to be a little more careful. Okay. Scroll down some more. Okay, so now that we've kind of gone from from equation to graph, I'm going to go the other way now. From graph back to the equation. So here it says, what is the equation of the transformed graph g of x? Well, since the g of x is the transformed graph, well, that means our f of x here must be the original, or what we call the base graph, right? In this particular case, you can see that, hey, it looks like it has flipped or reflected vertically. And since what we looked at was a vertical reflection, let's write that down. And vertical reflection, so our g of x is what it becomes. This is our transformed one. So our original, with a vertical reflection, the negative is outside the function. So you'll have the negative sign, and our f of x was multiplied by -1 to get us our new function. Another way to write it, though, instead of f of x, is to actually put that absolute value to replace the f of x. Remember, the negative sign must still be outside the function. So there it is. So two ways of writing the same thing. Okay, so let's scroll down a little bit more. It's not scrolling here. Oh, what am I? Oh, there we go. Okay, so last one here. So same thing, still the same question. So what is the equation of the transformed graph, g of x? So g of x is still the transformed one. Now, when I look at this graph, I am seeing a vertical expansion. So that red graph is pulled upwards from the blue one. So, you know, I'm thinking of it's kind of been pulled upward like so to make it looking like that. So let me write that down. I'm saying that there's a vertical expansion because it's, oops, can't spell, expansion. Now, how is it vertically expanded? We need to figure that out. So we'll need to be comparing some points. With vertical expansions, you cannot compare points that are on the x-axis because you're just comparing y equals to 0 with y equals to 0. That's not going to tell you anything. So you have to find a point. Let me just write that down. Find points not on, I guess, axes. X-axis in this case. Okay. So you have to compare 2 points. So if it's pulled vertically, we're going to compare 2 points that are kind of on top of each other. So we'll say, well, this point right here, we can see has vertically been stretched or expanded in this case to that point right there. So let's use our mapping to figure it out. So we know that we have 2, 2, and now it's 2, 6. Please be mindful that each box actually represents 2 here. And since we know this is an expansion, that means we have x, y is now, well, 2 did not change, so it's still x. And we know the relationship between 2 and 6 must be multiplied. So we know it's something y. Now, if y equals to 2, then 6 is 3y. So we know that 3 is our scale factor for the expansion. So this is our scale factor. So to write that down is our g of x. Remember, for vertical expansion, this scale factor goes outside of the function f of x. Or another way to write this, again, we can replace f of x by the absolute value. So 3 absolute value x. So at this point, I would like to challenge you to think of an alternate equation for this same question. There's still another way or another equation you can write to represent this one. So that will be my challenge for you. And that's it for 1.2.